Hi everyone, welcome to section 8.9 where we deal with some applications that involve rational expressions. So my hope is that some of these applications are going to feel very familiar when you compare what you learned in prerequisite courses. So this is the course equivalent. Math 85 is the course equivalent to Math 20-1. So when you were in Math 10C or Math 75, you would have dealt with applications that are very similar. So my hope is that these feel familiar. Let's take a look at our first example and we'll discuss the formulas that can be used to tackle each of these problems and make sure we set up those equations properly. We're going to give our first application a little read here. It says, if Donna can mow a lawn in 3 hours and it takes her sister Susan 4 hours to mow the same lawn, how long will it take them if they work together? So this is something I call a work rate problem. When we talk about work rates, and we're just going to do a little bit of a preamble here just to remind you about how to think about a work rate. If we take a look at work rates, basically what we're saying is how many jobs or what is the number of jobs you can do divided by the number of hours it takes you to do something. So when we talk about work rates, we want to think of it kind of like jobs divided by hours. So if I take a look at Donna's rate of work in this situation, it says Donna can mow the lawn in 3 hours. So she can do one whole job in 3 hours. Another way to think about this rate is that she does a third of the job every single hour. Susan, on the other hand, takes a little bit longer, so we can say that Susan's rate is different. Susan does one job every 4 hours, or we can say that she does a quarter of the job every single hour. Now, what we're trying to find is how long it will take them if they work together. So what we want to do here is let x equal the time together. So this is going to be the number of hours that it would take them if they were working together on the same job. So I'm just going to put in brackets here that this is going to be measured in hours. Now there's a standard formula for these kinds of problems that I like to practice with. So that standard formula looks something like this. If you have rate number 1, so whether it's a person or a machine, if you take that first person's rate or that first item's rate and you multiply it by the time together, and what I mean by that is the time they're working on the same task together, you can add that to rate number 2 or the second person's rate multiplied by the time they're working together. Sometimes that's going to be the same amount of the time, like we have in this case. When you add those two pieces of information together, you should get one complete job. So let's use this formula to see what's happening with Donna and Susan mowing this lawn. So Donna's rate, we'll say that is, in this case, rate 1. So rate number 1 is going to be 1/3. If we multiply that by the time it's taking them together when they work, they're working for the same amount of time. We just don't know how long that is. We know that that was assigned as a variable of x. Plus, we're going to add the second person's rate. So Susan's rate in this case is 1/4 multiplied by the time they are working together, which again is going to be x. And when we combine those, we should get one complete job. So this just becomes a small little rational equation for us to solve. And we know that we can solve this by clearing fractions. So if we pay attention to the LCD, we see that the lowest common denominator in this case is 12. So I'm multiplying every single term by 12 in this equation to keep it all balanced. And when we multiply by 12, 12 divided by 3 is really 4. So we have 4x in that first position. 12 divided by 4 is 3, so we have 3x left in that second position. And don't forget about that sneaky little 1 on the right side. 1 times 12 is going to give you 12. This just becomes a tiny linear equation for us to solve. So 4x plus 3x is 7x's. And if that's equivalent to 12, then to solve for x, we need to divide both sides by 7. So what we get here is x is exactly 12 over 7, but because this is an application, it's a little bit awkward to say this is 12/7 of an hour. So what we want to do is change this to a decimal number and we'll convert that to hours and minutes. So if we make this a decimal number, we know that x is approximately 1.71 hours. So in order to take and convert that decimal number of hours into minutes, we know that we've got 1 hour. So I'm just going to write that down. So 1 hour here, clearly because it's 1.71 hours. And to convert this last little 0.71 to minutes, what we're going to do, and I'm going to carve out some space in the left margin here, but if you take that decimal number of 0.71, and we know those are 0.71 hours, if you multiply that by 60 minutes, you're going to get the total number of minutes in this case as well. So when you take 0.71 and you multiply by 60, you get approximately 43 minutes if you round up. So in this case, we can put this together with a sentence and say it would take Susan and Donna 1 hour and 43 minutes to mow the lawn if they were working together. So our answer makes sense because one person on their own takes 3 hours or 4 hours to do the job. So, logically speaking, it would take them less time working together. So again, make sure your final answer is clearly stated in a nice proper sentence or statement. Our second example is another work rate problem, so let's give it a read. It says, it takes Sam and Greg 3 hours to do a job if they work together. It takes Greg 4 hours to do that same job all by himself. So how long would it take Sam to do the job by himself or to do the job alone? So in this case, what we have to be very mindful of is what we assign for variables. The question is, how long is it going to take Sam to do the job alone? So what we're really looking for is part of Sam's work rate. We know that Greg and Sam together do the job in 3 hours, but Greg can do this by himself in 4 hours. So what I hope you're getting out of this is that Sam takes a really long time to do this job. So if we start mapping out some of these variables or some of the information we're given, we know that Greg's rate is going to be 1/4 because he can do one job every 4 hours, or you can say he does a quarter of the job every hour. Now, the time that they're spending together in this case, we know is exactly 3 hours because they're working together on the same job and we know they're done in 3 hours. What we don't know is how long it takes Sam to do the job all by themselves. So Sam's rate is going to look a little bit different. Sam's rate is going to be one job in X hours. So what we can say here is that X is representing the number of hours it takes Sam to do the job all by themselves. So we can still use our same formula where we have rate number 1 multiplied by the time together, and then we add that to rate number 2 multiplied by the time together. And all told, this is going to give us one complete job. So if we talk about Greg's rate as rate number 1, we've got 1/4, but this time we know it takes them 3 hours working together. So instead of time together, we're going to replace that with what we know to be 3 hours. Plus we now have Sam's rate, which is 1/x. If we multiply that by the time together, which again we know is 3 hours, we should have a sum of one complete job. So this is another rational equation for us to solve, but the LCD this time is a little bit different. If you prefer, actually, we can rewrite this as 3/4. So if you multiply these fractions through, 3/4 plus 3/x is equal to 1. Sometimes that's easier to find your LCD. So your lowest common denominator in this place is going to be 4 times x. So if you multiply every single term you have in this equation by 4x, we will keep it balanced. So 4's cancel, leaving us with 3x in that first position. And then in the second term, the x's cancel, so we have plus 12, and that's equivalent to 4 times x. So this is another little linear equation for us to solve. And we can see that if we subtract 3x from both sides, we'll get 12 equals 4x minus 3x. 4x minus 3x is just x. So x is 12. As we anticipated, Sam's work rate is really slow. He does one job in 12 hours. So remember, this is representing the number of hours we have for Sam to do the job all by themselves. So what we would say as a final statement is that it would take Sam 12 hours to do the job alone. So that's extreme, but remember, it only took them 3 hours when they were working together. So Sam wasn't given a whole lot of help. So as always, you want to make sure that your answer makes logical sense when we compare it with the application. And in this case, we see that Sam's rate was considerably longer than Greg's rate. Example number 3 is very different. It says, by increasing her usual average speed by 20 kilometers per hour, Sheila finds that she can cut her time on a 240 kilometer drive by 2 hours. So be cautious. Sheila's driving pretty slow here. But what we want to find is Sheila's typical average speed. Now, sometimes when you're coming up with your variable assignments, it's a really good idea to take a look at the last statement or the question that they're actually posing. In this case, they're saying find Sheila's typical average speed. So that's actually what we want x to equal. We want x to be her typical average speed. This is what we call a distance rate time problem. When we compare distance rate and time, there's a formula that can be used to pull these variables together. The distance traveled is always going to be equivalent to the rate of travel multiplied by the time you are traveling at that rate. So we know that if we traveled at, let's say, 100 kilometers per hour and we traveled for 3 hours, then 100 times 3 would give us 300 kilometers as our total distance. So that's the formula that we're going to focus on. But anytime I have a distance rate time problem, I'm going to set up a little chart with 4 columns. So the first column is going to talk about the trips. Then we're going to have columns for distance, rate, and time. So we have 2 trips involved here. We have Sheila's typical trip. So by typical speed, started erasing things here. So we have a typical trip with what we know to be an average speed. But then we say if she goes faster, things change. So we can call the next trip the faster trip. And we know that in a faster trip, she's going to increase her speed. But be mindful that if you increase your speed, you decrease your time. So I'm going to have 3 columns in this chart. 1 for distance, 1 for rate, and 1 for time in each of these cases. So we don't know Sheila's typical average speed. We know distance is going to be measured in kilometers. We know rate when we're traveling based on the rates we're given is going to be in kilometers per hour, and we know that time is going to be measured in hours. So if we want to know Sheila's typical average speed, that's going to be our x variable. So if you look at your typical trip average speed, her rate is going to be x. Now, aside from that, we know that she increases her average speed by 20 kilometers per hour when she does a faster trip. So the faster trip is going to have a rate of x plus 20. So her original speed plus an extra 20 kilometers an hour because she's driving faster. Now, aside from that, we know that there's going to be a consistency with the distance. We know in each one of these trips, she's traveling 240 kilometers. So I'm going to insert that in our charts as well. We know that the distance is 240 kilometers regardless of whether she's traveling fast or slow. Now, one of the points I want to make when you're doing a distance rate time chart is that as soon as you have 2 columns filled in, use those 2 columns of information to fill in that 3rd column. So if we were to manipulate this formula, distance equals rate times time, and I wanted to solve for t instead, we can take distance and divide by rate in order to get time. So in each of these rows, we're going to do just that. So for the typical trip, or the trip where she's traveling at an average speed, the time is going to be distance divided by rate. So we have a distance of 240 kilometers, and we have a rate of x kilometers per hour. For the faster trip, we know that if we take 240 kilometers, which is your distance, we can divide by the rate for the faster trip, which is x plus 20. Now we've filled in our chart and we're ready to put some of this information together in order to solve the problem. So there's one piece of information that we haven't accounted for in the actual application. Basically, if we go back to that initial statement, when Sheila increases her speed by 20 kilometers per hour, she cuts her time on the drive by 2 hours. So what we mean is the time is very different. If we take a look at her typical average speed or average trip, actually let's call it the typical trip. And if we really compare the time for her typical trip, if I were to subtract 2 hours, that would be the time for the faster trip. So this is a comparison. I know that her faster trip is 2 hours slower or quicker than her typical trip. Another way to say this is if I take her typical trip and I subtract the faster trip, and again, if we're talking about time in both of these cases, the difference between those is 2 hours. Sometimes I'll have students put this all together and they'll say, well, what if we take the faster trip? And again, we're talking about time, and I add 2 hours. That would give me the total for her typical trip. And again, this is all measured in time. So any one of these formulas can be used because we're comparing the two trips and the differential of 2 hours. So I'm just going to use our last option and say if we take the time it takes for her faster trip, which we know according to the chart here is 240 over x plus 20. If we take that 240 over x plus 20 and we add a 2 hour time crunch here, we will get the total time for her typical trip. Her total time for her typical trip is 240 divided by x. So this is going to be one version of the equation that we can solve in order to find x. In order to solve this rational equation, once again, you're going to find the lowest common denominator and clear all of these fractions. So the LCD has to include both x and x plus 20. So if we multiply our first term by x and x plus 20, you can multiply your second term on the left side by the same LCD to clear those fractions. And on the right side, we'll do the same. So x times x plus 20. At this stage, we want to be very careful with your canceling. We see that x plus 20 cancels in the first term, and you're left with 240 times x. In the second term, nothing cancels, so we have 2x times x plus 20. And on the far right side, we see that x cancels, so you have 240 times x plus 20 once again. So from here, we want to open up our brackets and solve this equation to see what we get. So 240x is going to stay so far, but 2x times x is 2x squared, and 2x times 20 is positive 40x. On the right side, we'll have 240x, and we'll add that to 240 times 20, which is 4,800. This is now a quadratic equation for us to solve, so we have to be a little bit careful with how we solve from here. So if I have 2x squared on the left side, I'm going to bring all of the x's to join it. Now we're going to subtract 240 from both sides, which would cancel the 240s, but we do have plus 40x still remaining on that left-hand side. When the constant of negative 4,800 moves over to the opposite side, it becomes negative 4,800. And if we set that to 0, we see we have a quadratic equation. You can factor 2 out to give yourself some smaller numbers to work with. So in this case, I'm dividing all terms by 2. And then you have your choice for how to solve this quadratic equation. You can factor it, you can use the quadratic formula, you could graph this function and look for the x-intercepts. The choice is really up to you, but in this case, it's actually not too terrible to factor. Instead of looking at the numbers 2420, I'm kind of thinking in my mind about numbers like 24 and 2 in that middle term. So x times x is x squared. Factors of 2,400 could be 60 and 40. And the difference between 60 and 40 is 20, which is what we want in that middle term. So if we have 1 plus and 1 minus, again, if you solve this using a different technique, you are welcome to it. You'll get the same answer, but we get two solutions here. We get x equals negative 60 when we solve, so we know that x plus 60 could equal 0. We also know that x minus 40 could be 0, so x equals positive 40. Now remember, we're talking about applications. And in this case, the variable, if we sneak back and look at your table, is a speed. It doesn't make sense for us to have a speed that's negative. So we're going to reject negative 60 and say that that's extraneous in this case because it doesn't make sense in the context of the question. So x is going to equal 40. And we know this is Sheila's typical average speed. So we're going to say this is 40 kilometers per hour. Now that we know she travels at 40 kilometers per hour on her typical average speed or typical average trip, we can go back and compare that and find other pieces of information. If you wanted to know how fast she travels on her faster trips, of course 40 plus 20 would be 60 kilometers per hour, and we could get the time elements as well. We could substitute x equals 40 into those time functions to get the amount of time that it takes her traveling for those two trips too. So at this stage, just make sure that you clearly state what that answer represents and explain that 40 kilometers per hour will be Sheila's typical average speed. So example number 4 is another work rate problem. It says Carissa and Wayne sat down to mark final exams. It took them 7 hours to mark the exams working together. If it takes Wayne 3 hours longer than Carissa to mark the exams on his own, how long will it take them working individually? So what we need to do is figure out individual work rates. So as a quick reminder, when we talk about Carissa's rate, this is going to be the number of jobs divided by the number of hours. And in this case, we have no clue. We've got one job in X hours. When we compare that with Wayne's rate in this particular case, we can see that according to the instructions, Wayne would actually take 3 hours longer to do the same job. So if we don't know what that work rate is, we can just put this in and say that Wayne's rate must be 1 divided by x plus 3 because it's whatever Carissa's work rate is plus an additional 3 hours to complete that same job. The only other piece of information that we have is that it's taking them 7 hours working together. So we would say the time together in this case, or the time it takes them to complete the job working together, is 7 hours. So now we go back to our formula where we say rate 1 multiplied by the time together added to rate number 2 multiplied by time together is going to be a total of 1 complete job. So rate number 1 would be Carissa's rate, that's 1 over x. If we multiply that by the time together, which we know is 7 hours, we can add that to rate number 2, which is 1 over x plus 3. Again, we multiply that by the time together, which we know to be 7 hours. And all told, that should be giving us 1 complete job. So just to clean up the fractions a little bit, we can say 1 times 7 over x is really written as 7 over x. 1 times 7 times over x plus 3 is really 7 over x plus 3. And that right side, don't forget about that sneaky little 1. So once again, we want to clear your fractions and find the lowest common denominator. So in this case, we see the LCD is x times x plus 3. So we need to multiply every single term by that LCD. So x times x plus 3 in every single position, including that far right side and that lonely little 1. So don't forget about the 1 on the right. In our first term, we see that x's cancel, leaving you with 7 times x plus 3. Then we've got plus the x plus 3's canceling, so we have 7 times x. And on the right, we have x times x plus 3. So if we open up the brackets, 7 times x and 7 times 3 give us 7x plus 21. And we're going to add 7x, and that's going to be equivalent to x times x and x times 3. So x squared plus x times 3 is 3x. What we have one more time is a quadratic equation, so I'm going to push all the terms over to the far right side. We'll have x squared, we'll have 3x. Now we have 7x and 7x on the left side, so that's 14x's. When we push it to the opposite side, though, we're subtracting those 14x's. And when we have plus 21 on the left, we can subtract 21 on both sides to move it over. So we get 0 equals x squared minus 11x minus 21. Once again, this is a quadratic equation, but I'm going to save you a little bit of grief and say that this is not factorable. It doesn't mean that it doesn't have a solution. It just means that the solution might be some irrational number. So in order to solve this equation, you have some options. You can graph and look for the x-intercepts, or you can use the quadratic equation and figure out what the solutions are based on the quadratic equation. I'm just going to skip ahead and say if we graph it and we find x-intercepts, so again, graph and find, you're going to find 2 x-intercepts in this case. One of those intercepts is going to be at approximately, now we have to use decimals here because we don't have an exact solution. So x is going to be approximately 12.7 as one of your solutions. Now the other solution you get, or the other x-intercept you find when you graph, is approximately negative 1.7. But again, if we're talking about the amount of time it takes an individual to work through these exams on their own, a negative doesn't make sense. So there's no such thing as negative time. So that negative solution is extraneous. What that means is 12.7 is the only answer we can utilize for this application. If you go back to what that x means, x is going to be the amount of time it takes Carissa working on her own. So we can say that Carissa on her own takes 12.7 hours. If we wanted to know, again, this is in hours, if we wanted to know how many hours it takes Wayne, all we need to do is add 3 to that total. So if you want to convert those hours once again to minutes, we know that we will have 12 hours. And if you take, over in the margin here, we'll carve this out. If you take 0.7 hours and multiply that by 60 minutes, you get 42 minutes. So 12 hours and 42 minutes would be the total time it takes Carissa in order to mark those tests. And we know for Wayne, it's going to take 3 hours longer than that. So we can say 12 plus 3 more hours is going to be a total of 15 hours. And again, 42 minutes. So once again, with these work rate problems, you just want to be very careful about how you assign the variable. The formula remains fairly consistent in each of these cases. The last example we have is another distance, rate, time problem. It says a car traveling 70 kilometers per hour leaves a certain intersection 45 minutes before a second car traveling 95 kilometers per hour. So they're giving us rates initially. They're also making some reference to times. So remember, in these situations, we want you to fill in a chart. We have what we know as car 1, or the first car, we can say, at that intersection. And we have car 2 that leaves later but drives a whole lot faster in that same intersection. So aside from car 1 and car 2, we want to compare the distance, rate, and time in each of these circumstances. So when you go back at the problem or look at the problem, I always say if you read the last sentence or read the question that they're asking, it gives you a hint on how to assign the variable. They're saying, how long will it take the second car to overtake the first car? So how long is it going to take before the second car catches up and in fact passes car number 1, assuming that they're not stopping anywhere in between? So that's giving us a hint that time is going to be a factor of x. So keep that in mind for a second. What we do know is car 1 was traveling at a rate, and again, rate in this case is kilometers per hour. Time in this case is measured in hours, and distance, of course, is measured in kilometers. So car 1's rate is 70 kilometers per hour. Car 2's rate, the faster car, is 95 kilometers per hour. If we want to know how long it's going to take for this second car to overtake the first car, we're going to start and say their time must be x, but there's a tiny little adjustment we need to make here as well. If you go back to the original explanation of this problem, it says a car traveling 70 kilometers per hour leaves a certain intersection 45 minutes before your second car. So what that means is the time that first car is on the road has an additional 45 minutes. But be careful, when we're dealing with minutes, we have to convert to hours to use this in our formula. So the time that car 1 is traveling is going to be x hours plus another 45 minutes, which we know is 3/4 of an hour. If you take 45 and you divide that by 60, so 45 minutes out of 60, you'll get 0.75 hours. So car 1 is traveling for x hours plus an additional 45 minutes, or 0.75 of an hour. Car 2 is only traveling for x hours. There's no adjustment that needs to be made for car 2. If you recall from previous examples, as soon as you have 2 columns filled in for this chart, use those 2 columns of information to fill in the third. We know that the relationship between distance, rate, and time says that distance is equivalent to rate multiplied by time. So if we take car 1's rate of 70 and multiply it by the time, which is x plus 0.75, that would be total distance for car 1. If we do the same thing for car 2, car 2's rate is 95 kilometers kilometers per hour, and their time is only x hours. So now we filled in the chart. We need to somehow use the information from this chart to answer the question. So what I want you to keep in mind is this seems a little bit tricky, but I'm going to do a little bit of a diagram on the far left side. Car number 1, and I can't draw, so we're just going to use a star, and car number 2 leave from the same space. If I could show you car number 1 starts traveling for 45 minutes, and then car number 2 starts to take off. What's happening is they're both traveling, but car 2 is traveling a little faster, so inch by inch, they're making up some time. At one point, though, car number 2 catches up to car number 1. What I want you to recognize here is that the distance car 1 has traveled is the same as the distance now that car 2 has traveled. So we can set that up as an equation. We can say the distance traveled for car 1 must at some point be equivalent to the distance traveled for car 2, because at that point we know one car has caught the other. Now go back to your chart. We know the distance for car 1 is 70 times x plus 0.75. So when is that distance going to be the same as car 2, which we know is 95 times x? This is going to be a small little equation for us to solve now. So open up your brackets. 70 times x is 70x. And then 70 times 0.75 is going to be 52.5. If that's equivalent to 95 times x, then we can solve this little linear equation. So I'm going to subtract 70x from both sides. And when we do, we get 52.5 equals 25x. And the last step, of course, is to divide by 25. So when we divide both sides by 25, we get x equals 2.1. And remember, x is referring to a time measurement. So really, x is 2.1 hours. Once again, if you want to convert this to hours and minutes, you can take that 0.1 hour and then multiply it by 60. So you'd get 2 hours and 6 minutes. So in this particular case, after 2 hours and 6 minutes of driving, car number 2 is going to have caught up to car number 1. Now, if you wanted to figure out how long car 1 has been on the road, car 1 has been on the road a little bit longer, and you can see that in your chart. They've been on the road for 2 hours and 6 minutes plus another 3/4 of an hour. So car number 1 has actually been on the road for 2 hours and 51 minutes. So again, it's going to take 2 hours and 6 minutes for car 2 to overtake car number 1. So 2 types of problems we explored in this section. We dealt with work rate problems and distance rate time problems. Now we'd like you to have a look at the regular homework and see if you can practice with a few of those formulas. As always, if you're having any issues whatsoever, please make sure you reach out because we're always happy to help.